Welcome, everyone. Thank you for joining us today for our mid-April working group meeting. I have to remind you that the meeting is being live streamed on YouTube and it's being recorded, and those recordings will be available later. Our speakers have very generously agreed to stay on for a half an hour after the end of the meeting for an informal discussion. And depending on how you feel about it, we'll either have a free-for-all in the main discussion room, or I've created some breakout sessions which we could use for individual discussions. As usual, I introduce myself, James Glazier, Reinhard Labenbacher, Jim Sluka, who's on the call, and Bruce Shapiro. And we're always available to take your suggestions, critiques, comments, and so on. So please feel free to talk to us. You've also seen this slide many, many times. We do have a Slack channel. We have a Twitter. We have our IMAG MSM wiki page, which always needs love and work. We now have a IMAG LinkedIn page, and we have a YouTube channel that archives all of our videos. And so we'd appreciate your help using these means of communication to get the word out. We also have a Facebook page. So people who are more savvy about social media than I am are would be much appreciated if they want to participate. Starting with a few weeks ago, we had the opportunity to have short announcements. Does anybody have a short announcement that they would like to make before we get to the main business of the meeting? I'm looking to see Jacob, go ahead.
Yeah, for those who contributed to the white paper of the integration and credibility reproducibility group, please vote. We have 2 votes currently, one from James, one from John. If you want a different venue, please vote. It's on our mailing list. Tonight, it's like in about 12 hours or 11 hours is the deadline to vote. Please vote.
Thank you. Any other announcements? Well, I have one announcement, which is that we're going to have our annual CompuCell virtual tissue modeling course. We're going to be teaching it online. It will be the first week of August. We'll have 5 days of classes about how to build multiscale models, followed by a 2-day hackathon. That was a format that worked very well last year. Anybody who would like to learn how to build multiscale models in CompuCell would be welcome to participate. Over the years, we've had everything from high school students to emeritus professors and everything from pure mathematicians to surgeons take this class. We'd love to have people join us. This year, there's also going to be a class the week before that on Paul Macklin's Physicell modeling methodology. And following tradition, the week before that, Herbert Sauer is going to be teaching ODE, reaction kinetic modeling and stochastic modeling using the Telluria modeling package. So there are actually going to be 3 consecutive weeks of online tutorials and opportunities for people. We'd love to have your help getting the word out about these events. The other 2 will be announced more formally in the next week or 2. Any questions about that, please come to me, Jim Sluka, and if you go to the CompuCell 3D website, you can register and find out more information. As usual, we've got the request that if there's something good that's come out of this working group, you let us know about it so that we can document our successes and presumably improve. If you tell us about failures as well. And I'm not going to read the slide, you've seen it before, but anything that you feel is useful to document coming out of the working group would be much appreciated. Our schedule for upcoming meetings, I'm very excited that next week we have Deborah Peters from the USDA talking about predictive modeling in animal diseases. Very beautiful, very elaborate and extensive modeling with tremendous experimental validation. Donald Coombs is going to be talking about digital patient projects, so very medical. application. That's going to be very exciting. He's joining us this week on the call. We appreciate that. The following week, we have Penelope Morell and Catherine Morse. That's going to be interesting because they're very different topics. Penelope will undoubtedly be talking about unsolved problems in immunology. Catherine will be talking about standards and standards development from the point of view of somebody who's done that extremely successfully, not in particularly the context of biomedical modeling. And then going forward, you can see the schedule. As always, we would love to have your suggestions for future speakers. If you are a subgroup leader and you would like to present your successes or issues, we would very much appreciate you doing that. I also want to remind people who are subgroup leaders who feel they should be part of the steering committee that we have a steering committee meeting tomorrow morning at 11 a.m. If you need to have the link and you don't have it already, please contact Bruce or one of the other leadership for that. One of the things we're going to be talking about, I believe John Rice is going to be talking about organizing the next IMAG MSM PIs meeting and how that should be done. And that'll be exciting to hear about. As usual, during the meeting itself, because we're on a tight timeline, if there's time for questions, that's less of an issue now that we have the discussion group afterwards. We'd like to make sure that the questions are generic and short. I will give people a 5-minute warning. That is, after 15 minutes of your talk, I will break in and say, you have 5 minutes left, because it's hard to stay to 20 minutes. But we want to make sure that both speakers have able time to complete their full talks during the period that we have. So without more ado, I will turn the floor over to Winston, who is going to be telling us about a theory for multiscale modeling of disease dynamics. I guess if I could ask people to mute if you're not speaking, that would be very helpful. Winston, I'm going to stop my share and you have the floor.
Okay. Right, can you everyone hear me?
We hear you.
Right. Okay, so I can talk. Thank you very much for giving me the opportunity to speak to such a large group of people interested in multiscale modeling of infectious diseases. I have been working on this topic for some time now, I think since 2013. Apart from this theory, which I'm going to discuss with you, I've also developed some models and a method for integrating scales. But most of my work is about only integrating 2 scales. And so I'm going to share with you a theory that formalizes some of the knowledge about multiscale modeling of infectious diseases. I will have only about 4 segments of the presentation. I will discuss a little bit about what a theory is, and then I go into the theory and discuss some of the terminology that is used in multiscale modeling of infectious diseases. And of course, I will speak a little bit about the validation of the theory itself. So the word theory has everyday use and is also used in science. Well, in everyday use, it is taken to mean some guess that has no supporting evidence. But in science, it is a well-substantiated explanation of some natural worlds that might include laws and hypotheses. So then, as a result of that, a theory would be able to provide some basis for making predictions about what we observe. Now, there are different ways of developing a theory. If there is someone wants to give effort to developing a theory. Four main approaches are useful for developing a theory. Maybe you might use one or a combination. So one of it is that you make observations. Maybe you have data that you have and you do some analysis of the data. And based on that data, you interpret it and analyze it and come up with theory to explain the data. Or you might be extending or modifying an existing theory to explain new context, such as what might happen here, that we have already a transmission mechanism theory and we want to extend it to explain new phenomena about disease dynamics. Or you might be applying an existing theory into some entirely new discipline and you have identified some similarities between the new discipline and the theory that exists in a totally different discipline. But also you might consider a combination of these, and I shall highlight how I have used a combination of these to come up with a theory, or the theory for multiscale modeling of infectious diseases. So based on these, a number of theories, some of these approaches, we can talk of information theory, Shenoy, and game theory, John, and then we have a number of theories that have been developed to generalize or formalize knowledge that is already well known. We have relativity theories by Albert Einstein and of the theory of evolution by Charles Darwin. So in terms of infectious diseases, there has been very little development of theories of trying to explain disease dynamics. What has happened is that I've tried to look at it and identify that probably there are only two theories that have been developed in the past. One of them that has informed the modeling is the infectious disease causation theory. This is not a single theory, but a group of theories that were established and continuously refined to discuss the causes of infectious diseases. Of course, at the start, people didn't have much scientific knowledge and talked of the diseases as being caused by demons, and others may be saying that this is a punishment from God, up to the germ theory, when science began to chip in to explain the causes of infectious diseases. And now we have the epidemiological triad theory, which is the final theory that we all agree that this is what causes infectious diseases. So, and it talks of interaction of host, pathogen, and the environment cause infectious diseases. Now, but then we also have the transmission mechanism theory. This theory highlights that transmission is the only main dynamic disease process that we have to incorporate in multiscale models of disease dynamics. And so at every level of an infectious disease that you want to develop a model, you just only incorporate transmission. And then this is normally done by, obviously, many people have done this by classifying either you are at tissue level or at cellular level, you just classify them into a number of homogeneous classes and you develop models to explain that. But then the actual transmission, the main mechanisms of transmission would be environmental transmission and direct transmission and vector-borne transmission. And these are the transmission mechanisms that have been incorporated into multiscale models, with transmission as the only main dynamic disease process. And this has happened for quite some time. With direct transmission, we have the famous SIR model and some variations of that. With environmental transmission, the only additional aspect is a variable that describes pathogen load in the environment. And vector-borne is a combination of those, except that you have two hosts, a vector host and vertebrate hosts. Now, these ideas of transmission theory started off with Bernoulli and were continuously refined by Kermack and McKendrick into what we use these days, the SIR model and its extensions, including just a few aspects of it, but almost all of the mathematical biology has been based on this SIR model. Mathematical epidemiology has been based on this theory, transmission theory with the SIR model with a few extensions of it. But there's limitations to this theory, transmission mechanism theory, is that it is not capable of providing a systems level description of infectious diseases. And this is especially for processes of disease that happen at varying times and space. And so because of that, I also proposed this replication transmission relativity theory, which caters for both transmission and other processes that are relevant to disease dynamics. So transmission is just one process that happens in disease dynamics, but there's also pathogen replication or reproduction that leads to transmission. So because then we also have transmission and we have replication, that's why I called this new theory of disease dynamics the replication transmission relativity theory. But the relativity aspect I will explain shortly. Now, in a statement, this theory states that at every level of organization of an infectious disease system, there is no privileged or absolute scale which would determine disease dynamics. And you have to consider the interaction of both the microscale and the macroscale in developing models of disease dynamics. What it actually does is that this theory is that it acknowledges that at every level, both the macroscale and the macroscale, there are two different processes that influence each other in a positive, through a positive feedback mechanism. So at the microscale, that's where we normally have pathogen replication. And at the macroscale, that's where we have pathogen transmission. And these two processes influence each other in a positive feedback mechanism. The issue is that these two scales, what they do is that there's half a cycle which is about the transmission, and that happens in one scale. And then there's also another process at the microscale, which is replication. So you have a cycle which transcends which goes across two scales. And that will be a multi-scale cycle in disease dynamics. So when we are actually develop simple multi-scale models, we are considering this multi-scale cycle which goes across the microscale and the macroscale. So this theory, the relativity aspects, comes from the fact that it can be considered as an extension of relativity principle in physics, which states that there is no privileged frame of reference from which to determine motion of objects. That is when you are considering position or location, velocity, and acceleration, that these are relative. There's no absolute frame of reference from which you can consider these quantities. Now, this also can be, this relativity theory, replication transmission relativity theory, can also be considered as an extension if we then take the microscale and the macroscale as representing two different frames of reference. So this is basically the short of it about the theory itself for multiscale modeling of disease dynamics. But there's terminology that I've consistently used without giving explanations of it. So there are 5 terms that have a special meaning in this theory. It is the word system, subsystem, level, and scale and component. What happens is that because a disease itself is a complex system, you have to bring down that complexity by decomposing it or discretizing it. And obviously from the complex system itself, the first discretization would give you subsystems, which are the 3 subsystems: the pathogen subsystem, the host subsystem, and the environment subsystem. And below that, you have the level, which is a level below a subsystem, and then we have a scale. But this definition is only applicable to the theory. You can't apply this discretization and the meaning of these words to all complex systems. Because of that, I have tried to, in order to accommodate these aspects, to say complex systems are of 2 different types. We have what are called functionally organized complex systems, and we have what are called the structurally organized complex systems. And structurally organized complex systems are the ones that can be considered under this consideration, where you have system, the whole complex system divided into subsystems, and then a level, and each level would have 2 scales in this context of structurally organized systems, where you have a microscale and a macroscale. So in this case, a level is considered a layer below a subsystem in the subpartitioning or in the hierarchy, and a scale is also considered a layer below a level. But so when you consider a subsystem or a level or a scale, you would say each of these is a component of an infectious disease system. Now, the most important aspect that is important for the theory is that while levels and scales are used in this partitioning of a disease system, levels are assumed to be loosely coupled, while scales, remember I said that each level has 2 scales, a microscale and a macroscale. So between the levels, there is loose coupling, but within each level, there's a strong coupling between the scales within a level. And this, because of this, we can analyze, because of this assumption, we can then analyze each level independently. So how do we, what are these levels that I've been talking about? This is just a summary of what I've been talking about, that we have subsystems, which is the pathogen subsystem, the host subsystem, and the environment subsystem. And when you consider the interaction of these subsystems, you then have about 7 main levels of organization of an infectious disease system, which run from the cell level, the tissue level, the organ level, and the micro ecosystem level. And this organ level can also be called the micro community level, because you can consider each organ as a community of pathogens. And then the micro ecosystem is when we consider that there is multiple infections among the micro communities. And then we have the host level, and then the community level. This is when you consider that the environment, the geographical environment is heterogeneous, and you therefore discretize it into various communities. Like you say that COVID transmission is different among the states, say, or among provinces, or among different cities. Then you discretize into various communities. So you have the community level. And the macro ecosystem level is when you have the different communities, but with multiple hosts and multiple pathogen infections. And
Just
as I've said earlier,
5 minutes.
all right, I think I'll be able to make it. Thank you. So this is the discretization I have been talking about, about an infectious disease system, which allows us to use that theory that you have these 7 main levels of organization. I'm not sure whether it's clear, but it is exactly what I have said, that you have the cell level, the tissue level, the organ level, micro ecosystem, all the way up to the macro ecosystem level. Now, you cannot consider the molecular level here because what is happening at each level, these levels are considered the lowest discretization of a complex system, and each level exhibits the complexity. So it must have the 3 things that are involved in an infectious disease system. That is the pathogen, the host, and the environment are considered at each of these levels. So you can't go below the cell level. So then with this, we have 3 main levels, which we can group all those 7 levels because of the multiscale cycles that are involved into only 3 main levels. This is the primary level, which consists of the host level and its sub-levels. That is the cell level and the tissue level. And then you have the secondary level, which consists of the micro community and the macro community. And finally, the tertiary level, where you consider the ecology and evolution of infectious diseases. Then with this, corresponding to those 3 main levels, you have different multiscale cycles with different structure. You have a primary multiscale cycle, which you have to consider when you do the modeling, and you have the secondary multiscale cycle, and you have the tertiary multiscale cycle. So it depends on the complexity that you want to incorporate in your multiscale model. But effectively, the simplest is where you have a primary multiscale cycle, and obviously the most difficult is when you have tertiary multiscale cycle. Across these 3 main levels, I have worked to establish the main categories of multiscale models that can be developed. I'm not going, because of time, I'm not going to describe in detail how these different multiscale categories of multiscale models are different. But the first one, the individual-based multiscale modeling, is the simplest, and this is where most people who want to develop multiscale models do, because you don't explicitly incorporate the 2 scales that I have described to you. So it becomes the simplest. But these other 3 and going down are very difficult, and very few methods have been developed to develop multiscale models in these other categories. So because of that, we can consider an infectious disease system as consisting of only 3 component subsystems, levels, and scales. This is in the context of, I know, because most of the definitions of multiscale systems, particularly, have been informed by agent-based modeling, where they say it is consisting of a complex system consists of many interacting components, but this is not entirely true. It is just because of the method, which is agent-based, where there's several agents being incorporated into the model. But a complex system would have as simple as only these 3, say the host, pathogen, and the environment. But you also have this definition, which is based on properties of complex system, where you have openness of the system, the history of the system, and self-organization, which results in multi-scale and multi-level system. So I normally like to illustrate this complexity by a cartoon, by a story that I've read about the blind man and the elephant by John Saxon. This says that there were blind people who were asked to touch an elephant, and each touched their different parts. And when they were asked to describe what they see, they came up with different explanations of the elephant. And this is basically what happens when we do single scale modeling, that we are looking at a complex system and we don't incorporate the complementary information that comes from the different scales that are involved in the complex system. So then, perhaps, because there's no time, I just want to highlight that I have, using a method that I developed, tried to validate the theory, what I've done, because there's no time. This is a multiscale model for hookworm disease. Perhaps the two main points are this which is in bold, that is the linking from within host to between hosts. And the last one in equation 6, which also this first term, which also links the within hosts, and it scales down from between hosts to within hosts. So this method has been I've successfully used it to explain disease dynamics. What it does is that it actually gives you, when you work on it, the two reproductive numbers. And it's much simpler than the time since infection that is extensively used in multiscale modeling of infection. You actually get the two reproductive numbers, and you can see whether it is the replication, which is the reproductive number at the microscale, or it is transmission at the macroscale, which is contributing more to disease dynamics than the other. So this was the validation where we try to illustrate that even when you calculate the endemic equilibria, both the within host variables and the between host variables influence the same disease dynamics. So this is basically some numerical simulations to illustrate that. But this work I have presented is work of 4 main papers, which I have published over 4 years. So if I have left out any details, most of the information is in those 4 publications. They are general papers about multiscale modeling of infectious diseases. So thank you very much for listening to me, and I'll be available for further questions if you want clarifications at the end of the presentations. Thank you.
Thank you very much. We better move on quickly to Vivek, I think, and then come back for the questions at the end. That was still a very, very nice presentation. Thank you. So.
Sorry.
All right, so I'll share my screen then.
Yes, please go ahead. Let's see. Winston, there you go. Thank you.
Do you see my screen?
Not yet.
Okay.
There we go. Thank you. Take it away, please.
All right, very good. So, so Winston gave this nice example of the elephant. So I'm probably going to look at the trunk, or maybe even something at a smaller level. So what I'm going to be talking about is immune response and its impact on fibrosis. So in particular, I'm going to look at the interactions of macrophages and fibroblasts. So fibrosis has been a big topic of research and discussion in the past year or so because of COVID. So, so COVID-19 patients who develop pneumonia or ARDS, acute respiratory distress syndrome, usually, these symptoms eventually lead to pulmonary fibrosis in about a third of the patients hospitalized. You can see that in this, in these images from Spagnolo's work in Lancet. So after 3 weeks, you see this deposition of collagen in the lungs, And these fibrotic scars can be permanent, meaning, so they could persist even after the individual recovers. And it could have long-term ramifications, many of which are not known. People are still looking at it. So what is giving rise to this sort of a process? So this is basically the wound healing process, where in response to injury, there are inflammatory mediators that bring in immune cells such as macrophages, T cells, neutrophils, etc. And these cells release cytokines, primarily TGF-beta, which can then activate fibroblasts to myofibroblasts. So myofibroblast state is an activated state of a fibroblast. And in this state, it can produce the extracellular matrix required to heal the wound. But if the macrophages persist there, they can continue to overactivate the myofibroblasts, which can then lead to extra accumulation of the collagen fibers, or the extracellular matrix. And so this is what is seen in these patients. So the question that I would like to address is, how are fibroblasts able to attract macrophages? And so the question is it paracrine signaling, or is it due to the ECM? And as I'm going to show you, understanding to these questions can then lead to strategies for maybe mitigating fibrotic, the growth of fibrotic lesions. Okay, very good. So this is work done in very close collaboration with Boris Hinz, a good friend at the University of Toronto. So here, again, Winston brought up all these tissue models and things. Here, we are going to look at a really, really simple model where we have a collagen gel. And in that, you have a macrophage. It's a dilute distribution of macrophages. So you can just focus on one macrophage. And once you see this macrophage here in time, what's going to happen is that the macrophage is going to exert forces. And then what you're seeing here is the sort of the strain field created by the macrophage, if you will. And in time, after 18 hours, the macrophages remodel the surrounding the collagen fibers. And the collagen fibers, there's a high degree of alignment, okay? So when you look at this, if you're a physics or mechanics person, then this is a very surprising result, because the size of the macrophage is about 10 microns or so. But the strain field it is exerting is of the order of thousands of microns, which means the fibroblast is exerting fields over very large distances. And if you simply use a linear elastic sort of thinking, then this is not possible, because the only scale in the length scale in the problem is the size of your myofibroblast. So why do you have this long range propagation force? That's sort of the first question. Now the question is, how are these fibroblasts or myofibroblasts able to attract macrophages? So what Boris and his team did is they started introducing macrophages in this window in an hour, and they categorized the response to the macrophages into 3 categories. Attracted, meaning they will go towards the fibroblast. Responsive, meaning 50-50, meaning it's not quite persistent. It might take a different route. And then non-responsive means they go in completely random directions. So when the macrophages are introduced here in the first hour, you see that 68% are attracted. 3 hours, the number goes to 65. And then for larger time durations, like 18 hours, they're not responsive. This again is surprising, because the cues that attract cells are things like alignment, orientation. Cancer cells have contact guidance. They sort of follow the track, the track laid by collagen. So here the collagen is a lot more aligned, but you see that the macrophages don't go there. So the question we want to address is 2 questions. Why do macrophages, why do fibroblasts align collagen over these really large length scales? And what are the macrophages responding to? Are they responding to alignment, strain rate, and what's the mechanism? All right, so to understand this, you got to understand the mechanics, the interesting mechanics of fibrous systems. So to do that, what I'm going to create a network of collagen fibers and see how that network responds to force. And you're going to see there's some really interesting response to force that these things display. So to do this, there are many methods you can use. So I'm going to show you discrete model. You can also use sort of continuum model. So in this approach, we take a box, we put in collagen fibers. Every time they intersect, we cross-link them. And in this way, you can create a network. Now, each of these fibers, are like this wire. They can both stretch and bend. So they're basically semi-flexible, okay? And now what we can do is we can make it look like the real network in terms of the fiber density, the stiffness, and so forth. All right, now I'm going to show you the really interesting response of this material. So now if you deform this in shear, you see that initially the fibers are completely random. But as you deform it in the direction at a roughly 45-degree line where there is high tension, the fibers align. In the orthogonal directions, the fibers buckle. As a consequence, you're able to really align these fibers. And aligning means what you've done is you've taken something that is bent and stretched it out. If I stretch it out, it's even harder to stretch. So a prediction of this model then is that this material should show what's called strain stiffening, which means if you look at the shear modulus and plot it as a function of shear strain, you see that these materials will stiffen. In fact, if you look at this network, it's stiffened by a factor of 100. So really, these are highly strain stiffening materials, and these are our predictions from theory. And the red and these dots are measurements that are reported in this article. Now, what we can do is we can actually ask how cells remodel this matrix. So to do that, you can take the same network, put in a cell there, and exert a force, a contractile force. And now what you can see is that these, the cell actually remodels the matrix. So here, the way I've color coded these fibers is that red is, strains above 1%. Gray is strains between 1% and 0%, and then blue is things that are buckling. So you see the direction orthogonal to the direction of force, the exertion of the force, you get buckling. In the other directions, the fibers align. And in this manner, this nonlinear mechanics really allows communication over very, very large distances. Now, coming back to our experiment, so what we can now do is keep increasing the amount of force exerted in time, and then really see that with the increasing force, you have more and more regions over which the displacement is going to propagate, and that really beautifully agrees with our measured data. And now, so the question is, what's leading to this sort of a process? So again, I don't have time to go into it. So we've been working on the cell matrix crosstalk through a series of these articles that I've shown here. So the idea here is that the cell will exert a force that will align or stiffen collagen that feeds back through enhanced mechanosensitive pathways, which will further enhance contractility and so forth. And finally, you will reach a steady state where there is tensional homeostasis, which happens roughly around this time. So without going into too many details, so the point is that this cell sort of behaves like a muscle. So there is a stress-strain rate relation. When the stress is small, the contraction rate is large, whereas when you reach stall stress, there is no contraction. This means in time, while the strain increases in magnitude and also increases in its range, the strain rate actually goes down in time. So after 1 hour of remodeling, you get very high strain rates close to the fibroblast. And when you go away from the fibroblast, the strain rate goes down, and in time, it starts decreasing. So this clearly suggests that the cells are actually responding to the strain rate as opposed to the orientation or strain. So why is that? So that's what I'm going to cover in the next 5 minutes before I finish. So here now so the focus has been on the fibroblasts, the highly contractile cells that produce the extracellular matrix, and how it's generating these strain fields. Now the question is, how's the macrophage going to respond to this strain field? Now, to do this, we're going to use a very simple model called the motor clutch model, which has been studied pretty extensively for the past 15, 20 years. So we're going to use this formalism that we've adopted, we've developed in this paper here. So the main idea is for the cell to spread, it has to polymerize actin. So you see here, there is a polymerization speed because this network that I've just shown here as one filament, it's really a network that's growing. So how does the cell control it? Cells have got active mechanisms through which can exert forces. So there are myosin motors which actually pull this filaments back through retrograde flow. So there is the polymerization, there is the retrograde flow. The difference between that gives you the spreading speed. Now the question is, so what else can you control? Clearly there are adhesions. So now as the myosin motors are pulling this, the adhesions will resist this pulling force. And if you can regulate that, then you can regulate the spreading speed. Now what will then determine how how this process is regulated? Clearly it depends on the stiffness of what is underneath. Because if you think about what the viscosity is basically a stiffness times a time scale. So the viscosity should scale with ECM stiffness. So the work done in the last 15, 20 years has shown that cells spread on substrates that are stiff or in materials that are stiff. So clearly, this shows spread, this brings in sort of that alignment. It has not brought in the rate yet, but clearly it has brought in at least a stiffness to start with. So now the question is, this is spreading, how does a cell move? So now if you think about this situation that I described, where you have a fibroblast here and this here is your macrophage, without this fibroblast here or in a highly isotropic situation, the spreading will be uniform on both sides. But that's not the case here. On the one hand, we know that there is more, there is a strain rate, which means this velocity is more than this velocity. So that means if you look at these two directions, the retrograde flow and this velocity, they are in the opposite direction. Here it is same. This means this actin filament can protrude more here. So this gives you sort of a velocity to move in this direction. In addition, the stiffness here is more than the stiffness here, because I said this is strain stiffening material. So if you now write down the effective velocity, then you'll get two components. One is that you get a speed that's proportional to the difference in Ke and K, which is in this alpha here. In addition, you get a contribution that comes from the strain rate. This is called durotaxis, means cells actually migrate to stiffer parts of the extracellular matrix or the tissue. And this is a new phenomenon which you have not seen yet in the literature. So you're yet to coin a name for it. Right. So here it is moving in the direction of the rate of deformation. All right, very good. So now we have a prediction that we can test because we have a strain rate here. And when I showed you that image earlier, so what Boris's lab has done is they put a bunch of beads in this collagen network, and they can see how the beads move. So you can actually calculate the displacement, strain rates, etc. So when you calculate that and put this on this graph, you see beautifully that at 1 hour of remodeling, this is just a strain curve with no fitting parameters whatsoever. You see this beautiful correlation with this, with the spreading space. So clearly, what's happening is these macrophages are responding to strain rate as opposed to strain. Okay, so how do we control it? Clearly, the key players here are the adhesions, which means if we knock off the adhesions in macrophages, in this case, the adhesion is an alpha 2 beta 1 integrin. So when you inhibit those integrins, the macrophages completely lose their directionality and they are no longer responsive. All right, great. What is yet another way of testing it, right? So here, I didn't talk about signaling. I didn't talk about any paracrine signaling, none of that stuff. All that we needed is a source that creates a strain field. So here, what you're looking at is a microneedle where we are sucking in collagen by application of a negative pressure. So this is mimicking.
5 minutes?
Yeah, sure. I'll take 2 minutes maybe. All right. So clearly the macrophages are seeing this strain and strain rate because you're pulling it at the rate, same rate as the fibroblast is pulling it. And now you can see this sort of directional movement. All right, so to summarize, single cell contractile macrophages can attract fibroblasts can attract macrophages over very large distances. In fact, 40 times their size, with diameters up to maybe a millimeter or more, which is important in a tissue context. And the macrophages perceive and follow the dynamic changes. So dynamics is really important of the fibrillar collagen via the integrin receptors, which then the important conclusion is that fibrillar collagen receptors then represent a potential molecular target for antifibrotic treatments. So the gist of this is that you need macrophages in the early stages of injury. But then if the macrophages continue to stay there, they can convert the fibroblasts, the myofibroblasts, to a much more activated state and then produce more and more collagen. So that's the story. Now, in the past few years, there's been a lot of recognition in the community that it is not just the mechanics, just the static properties, but really the viscoelasticity of these ECMs that's important. So in collaboration with my close colleagues, we just published this review article, which you can take a look at if you're interested. With that, I'll acknowledge my lab members, in particular, Ze Gong, who did the motor clutch work, and Ze is here, and Xingyu Chen, Xingyu is here, who did the work on collagen. And with that, I'll be happy to take any questions.
Thank you very much. That was a lot of work to cover in a short talk.
All right.
It's nice to see such beautiful biophysics as well. So we only have a few minutes left. I guess I will quickly just return the slide deck to the request for other business, and then we'll have time to chat after the canonical hour is over. Reinhardt, turn it over to you.
There's no additional business. I think that's that we need to discuss here. So I think we could move to questions as far as I'm concerned.
Okay. So we have opportunity now for questions from the audience for either of our speakers. Please feel free to break in and I have some for both, but I don't want to take the lead on it. So please go ahead.
I do see a question here from Ruchira Datta. So Ruchira, do you want to ask your question?
Yeah, for some reason I can't start my video, and it was a little tangential, but thank you for the very, very interesting talk. I found it very fascinating, and also have already recommended it to some other people who may find it very interesting. So the question was if the possibility of macrophage fibroblast transdifferentiation, which has been possibly shown in heart, at least in mice, and the possibility has been talked about for several years. Whether that may affect or be affected by the matrix reorganization, like there could be feedback to that phenomenon.
Yeah, thanks for pointing that out. This is the first time I'm seeing that phenomenon. This is the first time I'm seeing it. So I was not aware of that. But anything that has to do with the myofibroblast phenotype, which involves alpha smooth muscle actin, absolutely the matrix is involved. So we have a series of papers where we have studied this, but this is really first time I'm seeing this macrophage fibroblast transdifferentiation. So maybe some of that might be going on in the late stages of fibrosis. I'm not sure. So thanks for pointing that out. I don't have a good answer to your question.
All right, thank you. And yes, and thanks to actually both speakers for their talks, and thanks.
Lorenzo, please go ahead.
Hi. Thank you both for your talk. And a question for Vivek. I was wondering what you are shown some data on macrophages. If you have an idea what macrophage are they? So if they are specific ones, or if it works with every kind of macrophage, M1, M2.
Yeah, these are again, that's a good question. Right, in mathematics, we are just modeling it as a right. So so these are macrophages typically found in the lung. I can look it up in the paper. So right. So again, since it's a biophysical model, the main quantities of interest for us are the strength of the integrin adhesions, the polymerization, and things like that, which among many macrophages is similar. So we didn't pay particular attention, but I'm sure some of the details of that would be important, depending on how these variables are affected in the different macrophages.
Yeah, well, can you comment on how the macrophages were extracted? Or let's say you mentioned that they are from the lung, they were like primary macrophage from the lung. So I assume they will be kind of resident macrophage of the lung, which they are specialized and do their job there normally. They are not inflammatory, that's what I mean.
Right. I mean, so what we have only characterized is the biophysical response to these things, right? Because our analysis primarily is biophysical. So what I can tell you is that, and I'm happy to email you it's in the paper. I don't, on top of my head, I don't remember. But what we did is we took these macrophages, and others have done this too, and put this on substrates of different stiffness and see how much forces they exert. Right, and how fast they polymerize. Those are the only two things that are important for us at this level of modeling, and it seems to capture the data well.
Yeah. Okay, thank you.
All right.
John, please go ahead.
Yes, thanks to both speakers. I have one question for each. For Winston, in your definition of the pathogen, I guess it occurred to me that there could still be multiple hierarchies there, because you can think of a pathogen as a bacterium, but then you could also think of a bacteriophage as a pathogen of the pathogen. And then you might think of defective bacteriophages as still a pathogen of the pathogen of the pathogen. Are you thinking at all about these sorts of, you could call them ecological levels of pathogen, or hierarchical levels of how one defines a pathogen?
Yes, I think I did briefly explain that in one of the papers, because the linking of the scales is actually through the exchange of these pathogens across scales. So in that situation where you have a pathogen within a pathogen, then yes, there are those hierarchies, special hierarchies again, that okay, where you have phages and so on.
Okay, and then, oh, I'm sorry, yes. Was there further?
No, I said, yeah, those hierarchies, yes, where you have a pathogen within a pathogen, there are special cases that can be considered, because then at that level, you have to consider that pathogen as a host of the other pathogen.
Yeah, exactly. Yeah. And then I guess for Vivek, I think you were simulating the alignment of these of the extracellular matrix, and I wonder if the simulation was a 2D or a 3D model, and if it was a 2D, then does 3D is there a similar kind of alignment into the depth of the material, or how do you account for depth into the material sorts of behaviors of the cell that's on its surface?
Right, great question. So can I share my screen? It's 3D. Show a couple of images.
So it is a 3D model, if I heard.
Yeah. So John, so the thing is, you see this little image here, that's 3D. So everything that we did to produce the data here, I can blow it up here.
Oh, yeah. Okay.
But then if I run the movie here, you're not going to see it because it's much complicated. So just for the sake of illustration, I showed you, but all the models are 3D. including this. I'm not showing the depth here. It's all 3D.
Okay. So all the surface pulling.
What's that?
So all the surface pulling really propagates into the depth of the material.
Oh yeah, absolutely, absolutely, yeah, absolutely. And so now we have both discrete and continuum models, so we can actually do a full continuum stress strain kind of thing and get that as well. So there are two levels of modeling: a discrete one and a continuum one. Both give you the same result.
Very nice. Thank you.
I wanted to say that I really want to understand that those coarse-grained constitutive relations, because those microfiber calculations you're doing are extremely expensive.
Oh yeah, totally. Let me bring up, if you have other questions, let me bring up a slide where the math is there. Right, it's in a different presentation, so let me do that. And then I can explain. If anyone wants to ask Winston questions, just give me a minute. So,
because I would love to incorporate those into our modeling methodology, because we can't possibly do the single fiber calculation.
Absolutely. Let me just pull up a slide here.
So I want, while you're doing that, I'll have a question for Winston, which is, I thought it was very nice at the end. I'm sorry we didn't have a little more time. Because, of course, as you point out, people talk about R naught as if it were a property of a virus, whereas, in fact, R naught depends on the system that you're in. And I thought your derivation of the effective reproductive rates, which you didn't have a lot of time to talk about, was really interesting. And I hope we'll have a chance to have you come back and talk a little bit more about the structure of those models and which are the rate-limiting steps in different situations.
I would like to hear more about that as well.
So that would be, I'm sorry, I didn't hear who spoke up on that.
Me, William.
Oh, great. Okay. So let's let Vivek show us his response, and then we'll turn the floor over to, I'm sorry, Jacob, let's have William ask his question, and then Jacob, back to you, since there are multiple, okay? If you prefer to have people moved into breakout rooms, I can do it. These are very different talks, but of course you lose some of the dynamic.
I'm ready. I can show you the equations if you like.
Please go ahead.
Okay, yeah, it's here. So basically, if you look at this, network, right? So there are, say, two classes of filaments, ones that are more random and the other that are oriented. So now, if you look at finite elasticity, usually the way you write in a reference configuration, it's fully rotationally invariant. So you have to write it in terms of the invariance of the strain tensor, right? I mean, it's pretty standard stuff. But then you can, that's just, so there's this thing called I1, I2, I3, three invariants, the trace, the determinant, and the second invariant. So that's how you do it. But then an equivalent way of doing it is writing, as you can see here, in terms of the primary stretches. So the lambda are the three stretches. Okay, so there's a stretch in 1, 2, and 3 direction. Now you can write this, this sort of energy density. And then if you write the stress out of that, then you will get an equation like this, which means the primary directions of the stress and the strain are the same. So there are three principal directions. And your three principal stresses. So here I'm plotting strain, here I'm plotting stress. So the bottom line is that the fibrous component is actually the stress is really small below a critical level, and it rises sharply beyond that. So what happens is, though you start with a fully isotropic material, when you deform it in the direction of tension, you will get this. Now here, John asked this question. So these are the strain fields going into the substrate. This is a continuum model, and it looks exactly like the discrete model. And here there are two cells. If you use this any model out of the what's in the literature, you can't explain it. You need the fibrous continuum model. With that, you can explain this long range stuff. So it's in a series of papers. I'm happy to share them with you.
That would be great. I'd love to. Maybe we could meet separately, so I can learn, catch up. I mean, one issue that you face in some of these situations is if your cross-linkers are not permanent, then you have plasticity, and then your definition of strain you don't have a definition of strain.
Excellent question.
Because strain depends on the existence of a reference state.
Yeah, absolutely, absolutely. So can I share my screen again for a second?
Okay, sure. I'm afraid I'm doing what I suggested not to do, which is asking technical questions, but I'm so excited by this.
Right.
They're
so
both great talks, and I want to let, okay, go ahead.
Yeah, so it's the plastic deformation, right? So we've actually studied that, and it's exactly what you said. Again, I'm not going to go into the equations and things, but these crosslinks can form and reform. So you get plasticity, you get permanent deformation. So there is no definition of strain in that day. It's strain rate, epsilon p dot. But there is an elastic strain because there are elastic components. So you can combine the two. We've done that. But still, there's much to do. But we, I would say scratch the surface. Yeah.
That's very beautiful biophysics. We haven't had so many biophysics talks, so it's wonderful to have that. I appreciate it. Okay, let me go to William. You were very patient. Turn it over to you.
Yeah, no, I was just echoing what you said. I was also curious to hear more from Winston about the reproduction numbers and how that works.
Winston, are you there? I don't know if you could, looks like you may have lost your internet.
It froze. Internet.
Oh dear. I'm sorry, William, I lost your connection. Jacob, did you have a question?
Yeah, actually, I was about to ask something very similar like William to Winston, but and actually mention William because he's doing things that are related to exactly what I was about to ask. But since Winston is off, then I did have another question for Vivek. And Vivek, I am outside your field. I do things more similar to what William does. And I'm looking at what you're doing and can barely understand some of the language. I apologize if I ask something trivial and something that you may have explained, I just didn't get it. My question is, how do you validate? Because I see you have all sorts of assumptions of things that you think behave a certain way, a certain equation. Can you, in simple language, with a simple example, show me how you validate those things so I can better understand and explain later how those things happen?
Oh yeah, absolutely, absolutely. Right. So there were two parts of my presentation. The first is how are forces propagated, meaning you have a fibroblast sitting here, you got a macrophage sitting somewhere else. How is it going to come? How is it going to attract? So it has to send out these force fields, right? So we really need to validate, as you correctly pointed out, the models, right? Now, using microscopy, you can measure a lot of details of the collagen network. What's the fiber diameter, right? What's the mean spacing between crosslinks and things of that nature. So using such an approach, right, what we can do is, am I sharing or no? Right, with that kind of an approach, you can sort of measure the mechanics, which I've shown here. So what we have done is we have created a 3D network based on images, right? And then we do the stress strain tests that you see here. Maybe I should project it. And
so what you're showing me is actually the validation, like of your models.
Yes.
Okay, can you explain to me? Tell me like what the error is, so I will understand, and explain it as the simplest term there is, so I can understand.
Right. Yeah. That's a great question. Now the point is, I don't know which field you work in. There is a lot of.
I develop disease models. I don't go to the cells.
Right, which I've never thought about at all. But bottom line, a lot of these things are self-averaging. Means you do tests over a very large specimen, and you prepare the sample the same way. Your error bars are smaller than the symbols. So here the error bars are tiny, because these are macroscopic sort of collagen filaments that are obtained that way in this particular test. But maybe in this presentation somewhere else, there are error estimates on many of these things. So here, this is another way of measuring this, right? So let me. So here, what we did is we put a cell in here, and there are a bunch of beads, and then what these beads will do is they will displace, and these are the strain fields. Now you see the error. We have actually plotted these individual dots here, and the lines are our theory. So you can see, the error is, you can estimate what it is, right? So So this
So
is
the difference between the dots and the red line are the error?
Yes, the dots are the experiment. The red line is the theory, and the blue line is current theory. What is available currently? This is the new theory.
Thank you. So you're saying your theory is more accurate than the current theory, and you're showing me an example here. What happens
Right.
in between near the zero? I see that like you have two curves, but in near the zero there's nothing, and there are points there.
Here you mean? Yeah.
Yeah.
The reason is the theory is for the matrix. This is the cell. So the theory is for the matrix. We again we have a model for the cell as well, which will nicely connect it. I'm not showing it here.
Thank you. You explained very well.
All right. Thanks. Yeah.
Okay, great. Let's let William have his question now, and then we can come back. Thank you. William, go ahead.
My question. Do I have another question?
I guess you didn't get your
Winston's
comment or
back.
question. Yes,
Winston's
he's back.
back.
That's why.
Yes. Oh, right. Okay. I understand. Welcome back, Winston.
Okay. Sorry, I lost network.
No problem. No, I was wondering, similar to what James was wondering, if you could, you didn't get so much time to talk about what was going on with the reproduction numbers, and I'm curious what's going on there and how that works.
Yeah, what happens is that if you develop a single scale model at say if you have a within host model and between host model, so generally the within host model will have pathogen replication and then transmission between hosts. So what happens when you develop single scale models, you actually have those two separate reproductive numbers. But when you have a multi-scale model, those come out as a combined reproductive number, but you can see the different contributions of the different parts of the disease dynamics from the two scales. One of it will be a replication partial reproductive number, and another one will be a transmission partial reproductive number. So they all influence the overall dynamics.
Sure. Do you have a copy of the within host model running for each host, or do you have? Because you showed one system of ODEs there, and I was just trying to maybe even if you put that up on the screen again, it might help.
Okay. Yeah, they were. Let me try and share again.
You okay? Find it. You still on connected? All right.
I think I have a problem with connection. I don't know whether you can see this. I'm unable to share properly. Can you see this?
No, it's not sharing at the moment, I'm afraid.
Maybe I have to log out and join in again because I think I'm having problems.
Jacob, is there a question that you had for Winston that you wanted that doesn't require screen sharing?
It was very similar to what William was asking. So my question was related to the fact that he showed this Wiseman and the elephant, which is actually something that we all are coping with, but sometimes don't even understand that. But he actually showed it properly. It's like we don't see the same phenomena all the time. Now, I know that William, who asked the question, actually deals with this topic with composition. I deal with this topic of composition by using ensemble models. Winston, I know he works on this as well. And this is what I was about to ask him exactly. And it's very similar probably to what William asked because it has to do with how he composes those equations. I assume, maybe Winston can prove me wrong, but this was my question. I want to understand better how he solves the problem of the multiple Wiseman.
Yeah, it is based on based on scale. When you are moving from the two scales, there's scaling down and scaling up, which has to happen.
So your solution is at the level that merging scales?
Yeah, so because of the scaling up and scaling down, when you move from the higher scale, that is the macro scale, is scaled down to the
Can you repeat?
When you move up from the
Can you repeat?
micro
You got
scale, which is the lower scale,
disconnected.
you upscale.
Can you repeat? You got disconnected. You froze on our machines.
Okay, what I'm saying is that you get to downscale. Then when you move from a higher scale, which is the macro scale, you downscale the variables that connect the two scales. And when you move from the lower scale, that is the micro scale, you upscale the variables that connect the two scales.
So if I interpret you correctly, your wise men are looking at different scales, correct?
Yes, yes.
Okay, now I understand better. So in your case, it's looking at different scales. In my case, they're looking at the same scale. And William also has a theory about how to compose things. So this is why I'm asking this. It's difference between how we approach things.
I want to say something because I think it connects the two talks, which is that one of the problems in biology is that with certain very specific exceptions, boundaries are soft. There's a lot of boundary crossing. You don't have compartments. And so in computation, we have to define modules with strict APIs. But in fact, in general, we do not know what the information is that crosses the boundary of a compartment. And Vivek's talk was an excellent example of this. You have the cell changing its environment in a very complex way, and so that you can't derive what a physicist would call a simple constitutive relation. Well, Vivek's made progress in doing this, which is something people have been trying to do for a very long time. A simple constitutive relation that tells you what are the parameters or information that you need to pass from one scale to another. And if you don't know what the information is that you're going to expose at one level of your simulation to another, then you wind up having to model everything. And as an example of modeling everything, Vivek showed us these beautiful 3D fiber models, which are wonderful achievements in computation, but would not be practical to run in a large-scale simulation of what's happening over periods of months in the lung, for example, over length scales of centimeters. And so you have to see whether you could derive, and this goes back to your question, Jacob, also, you have to see whether you could essentially derive, in this case, continuum approximations that are good enough predictors of how these materials work. In the same way, we saw the microscopic mechanisms of how the cell is responding to its environment, but in a macro multicellular model, you would have a net cell movement. And the question is, how do you derive those approximate phenomenological equations from these beautiful microscopic theories when you have these very complex interactions? And Winston also talked about how you have these multiple scales. But if you're going to build a formal theory, you have to be able to build compartments with clean interfaces.
But James, you said we are not sure of the information. In this case, what happens is that, what I didn't clearly perhaps explain is that there is infection and shedding of the pathogen. So this is what makes the two scales share the pathogen. That from the higher scale to the lower scale, there will be infection, and then the lower scale sheds. For instance, if you consider the within cell and between cell, what happens is that the infection happens and goes through the cell. So that is going to the lower scale, that is the within cell scale. And then in turn, the cell sheds the virus or the pathogen, and that is excreting the pathogen to the outer scale, to the macro scale. So you actually know what is being shared between the two scales, that is the within cell scale and the between cell scale. All you need is that this information has you have to downscale and upscale as you transition the boundary between the within cell scale and the within cell scale.
Right, and I think that's a good point. You have, and I'm not saying that in your example that you can't do that. I'm saying in Vivek's case, he's showing that that kind of boundary definition can be very complicated or difficult, and you may have to think very hard. It could be many years, very large research project to define that boundary. As an example, maybe for your case, would be if you have an agent-based model and you have the viral load in the patient, the infectivity of the patient may depend on the viral load, but it might depend on additional information. It might depend on how sick the patient is. It might depend on social context. It might depend on where the virus was in the body. And so the infectivity that you use at that higher level might not be a simple function of the viral load in the patient. And then you would have to build a more complex model to explain what the infectivity of that individual was.
Yeah, you might have to incorporate more scales because, like I said, there's the cell level, the tissue level, the organ level, all the way up. So the higher the levels you choose, you will be actually incorporating also the lower levels. If you look closely at the multiscale cycles that I was explaining about.
Well, but this goes a little bit to what I was asking about. You know, about do you have a copy of this running in each individual? Because partly what I was getting at is, are all the individuals the same? And given that, as James says, it's really not just the biology when you get to the population level that matters. It's behavior matters very strongly. And is there heterogeneity among individuals?
Well, there are categories of multiscale models that consider heterogeneity. Like I gave you 5 categories of multiscale models, and the individual-based multiscale models are the ones that cater for heterogeneity. But the other ones, the nested, the hybrid, and the embedded are average-based multiscale models. So they don't consider heterogeneity.
I see.
So that's why the overall reproductive number is the overall reproductive number for the population rather than for each individual.
A reproductive number is actually defined as the number of people that you reinfect. This is like how much each individual gives to the other. So I think Winston is correct in here, but this number changes, like James said.
Right, it's an emergent property like fitness. It's not an intrinsic property.
John, you wanted something?
Well, I'm curious about the environment part. That if I'm looking from the perspective of the viron, the environments that I go through or my family does between the reservoir host, the transfer from the reservoir host to the vector host, survival in the vector host environment, survival in the environment between the vector host and the victim host, the human, and down to, we talk about the virus being inhaled in moisture drops, but then it's trapped in the nasal passage for a while. That's one environment. And then some of those things get down into the respiratory system, and that's a whole nother environment. And then some of them little suckers get inside of a cell, and that's a whole nother environment. And so you've got, when we talk about environment in your 3 parts, which I really loved. I mean, it was a joy to hear somebody talking about something other than the math, but the logic, but that whole sequence of, and is that what you have in mind when you talk about environment in the context of your theory?
Yeah, the environment changes at multiple scales because you have various scales. Each scale has its own environment. So there's one of the papers, is it the last one in the list of 4, where I considered how to determine the boundaries for these multi-scale models, because for this type of multi-scale model, you can explicitly define the boundaries, but they change depending on what you want to describe. For instance, if you are considering viral infections, you might describe the whole inside host environment at cellular level by just saying the overall viral dynamics is described by within cell and between cell dynamics. But you can also extend that to the organ level, where you say each organ then is a community of its own. So you have like micro communities within the host. So it actually depends on, but for like TB, you have to consider the tissue level, which is like the granulomas, which are the type of tissues that we consider, because what will be infected is the macrophage as a tissue as well. And also you have the within tissue, between tissue, but which will be like, say, a macrophage, which will be like a granuloma, which is the tissue that we are considering, because it is the one which is infected.
I was trying to see if I could make some of those levels fit into a fractal kind of thing. I mean, nature loves fractals. and are there, that when you look at it, each level, they may kind of have the same structure as you get down in successive levels, but the time is past. And
I hope that you, Jacob, you and John and Winston have plenty of time to chat. William,
that was
I
good.
thought having both talks were fascinating, and sometimes it's interesting to have 2 talks that are very parallel. Sometimes it's wonderful to have 2 talks that are very different. So I appreciate Winston and everyone's time, and we'll look forward to seeing some of you tomorrow. And the rest of you will see next week. Thank you, everyone, again, for participating.
Thank you for another good Thursday afternoon.
Goodbye. Thank you.